we will talk about how to use DFS to find biconnected components of a graph. Before we talk about biconnected components, we need to understand what a biconnected graph is. A biconnected graph is a graph that no matter which node you remove from the graph, the remaining of the graph will stay connected. For the left graph, if you remove this node, the remaining of the graph will stay connected. If you remove this node, the remaining of the graph will still stay connected. So the left graph is a biconnected graph. The right graph, however, is not a biconnected graph. Because if you somehow pick this node to remove, after removing this node, the remaining of the graph will be split into two pieces. So this is not a biconnected graph. In this case, the node we remove is called an articulation point or cut vertex. And after removing all articulation points, the remaining pieces are called biconnected components. As you can tell, the key to find biconnected components of a graph is to find all articulation points. And after removing all articulation points, the remaining pieces will be biconnected components. A naive solution to find all articulation points is to examine all nodes inside the graph. For example, we can check if we remove node 1, whether the remaining of the graph is still connected. And then we can check if we remove node 2, whether the remaining of the graph still stays connected. If we use depth-first search to check if the remaining of the graph stays connected, the naive solution leads to n times depth-first searches, where n is the number of nodes inside the graph. However, in fact, we only need one depth-first search to find out the articulation point. Let's first go through depth-first search. Assume we want to do the depth-first search starting from node 1. And we will follow the path to explore until node 3. From node 3, we will pick the path from 3 to 4 and until node 5. From node 5, we will find that the path to 3 and path to 1, both of them will visit a node that is still under exploration, so we will stop. But we will still draw the two attempts inside the right graph. At this point, node 5 and node 4 can be marked as visited. Node 3, however, still has a path that is not explored. Having done that, now node 3 can be marked as visited, as well as node 2. Similarly, for node 1, we still have one path to explore, which is from 1 to 5. Now, node 1 can be marked as visited, and the depth-first search ends. The graph on the right is called a DFS tree. The edges marked in yellow are called back edges. The brown ones we do not have any interest. A graph can produce many DFS trees. However, just based on any of the DFS tree, we can already tell whether there are articulation points. Here are two DFS trees. We do not know the two graphs which produce them. We can tell the underlying graph of the left DFS tree is biconnected because no matter which node we remove from the graph, the remaining graph will stay connected. For example, if we remove node 1, the remaining nodes 2, 3, 4, 5 will stay connected. If we remove node 2, the remaining nodes will stay connected. 3 is connected to 4, 4 is connected to 5, 4 is connected to 1. And similarly, we can check for node 3, 4, 5. And we can tell its underlying graph is biconnected. The right DFS tree, however, tells us that the underlying graph is not biconnected because if we remove node 3, then there's no way for node 1, 2 to connect node 4, 5. So we can tell its underlying graph is not biconnected. For both DFS trees, we will say the nodes are discovered in the order from node 1 to node 5, where node 1 is the earliest node that is discovered, node 5 is the latest node that is discovered. The key to find articulation points automatically is to check whether a node that is discovered later than current node can reach to a node that is discovered earlier than the current node. For example, in the left DFS tree, since node 5 is the latest node that is discovered, so it is automatically not an articulation point. And we will find that it can reach an earlier node, which is node 3. This finding will be propagated to node 4. Since node 3 is discovered earlier than node 4, so node 4 is not an articulation point. Comparing node 3 and node 1, it finds that the earliest node can be reached by node 4 is node 1. Again, this finding will be propagated to node 3. Since node 1 is discovered earlier than node 3, so node 3 is not an articulation point. Since it itself does not have any back edge, so the earliest node that it can reach is also node 1. This finding is still propagated to node 2, and similarly, node 2 is not an articulation point. And the earliest node it can reach is node 1. This finding again is propagated to node 1. For node 1, we need to check differently, so we put a question mark here. So for the left DFS tree, there's no articulation point. Again, we will repeat the same process for the right DFS tree. For node 5, again, it is the same. It is not an articulation point. And the earliest node it can reach is node 3. This finding is propagated to node 4, which tells us that node 4 is not an articulation point. But in this case, the earliest node that node 4 can reach is node 3. Again, this finding is propagated to node 3 because in this case, the earliest node that can be reached by node 4 is not earlier than node 3. So node 3 is an articulation point. And later we will find that node 3 can reach node 1. This finding is propagated to node 2. Since node 1 is discovered earlier than node 2, so node 2 is not an articulation point. And again, node 1 is the earliest node that can be reached by node 2. And this finding is propagated to node 1, but we need to check the root node differently. So for the right DFS tree, we can tell that node 3 is an articulation point. There may be more than one articulation point, but we only need one depth-first search to find them out. To check if a root node is an articulation point or not, we just need to check the number of branches that it has. If the number of branches is larger than 1, then it is an articulation point. Otherwise, it is not an articulation point. For the previous case, since it only has one branch, not considering back edges, so it is not an articulation point. However, if we selected node 3 as the starting point, the DFS tree that we will end up with may look like the DFS tree on the right. So in that case, because the number of branches of the root node, which is the node 3, is larger than 1, so node 3 is an articulation point.